Hello. So now we'll be solving the Leetcode question 230, kth smallest element in the BST. So we have given the root of a BST and an integer k, written the kth smallest element of all the values of the nodes in the tree. Okay, so this is the example. So there is one tree, 3, 1, 4, 2, and you have to find the kth smallest element. That is the first smallest element. So that is obviously 1. And maybe if we are given k equal to 2, then we have to output 2. Let's say this example as well. So in this tree we want to output the k equal to 3, that is the third last, or we can say the third smallest element. So it is obviously the first smallest is 1, second smallest is 2, third smallest is 3. So our output is 3. So let's look into this tree, and let's think about a simple brute force approach. So what if we traverse the tree and maybe a BFS or TFS method, right? So this is the starting point, the root of the tree, and so if we traverse the tree, let's say we store the values of the tree inside an array. So let's say 3, 1, 2, 4. So we are traversing this tree maybe with the DFS. Um, okay, and then what if we sort this array in an ascending order? So it will be 1, 2, 3, and 4. And then we just have to, do array of k minus 1. And that will simply give us, so let's say we want the second smallest element. So the array of k minus 1 will be 2 minus 1, that will be equal to 1, and a of 1 will be obviously equal to 2, right? So it's 0, 1, 2, 3. So it will be 2. So that's a simple brute force approach. And the complexity, if we see, so the space complexity will be obviously O of n, because we will be storing the n nodes, right? And the time complexity will be again O of n, because we'll be traversing each and every node of the array. So we can think of a better approach here. Oh, sorry. So time complexity will not be O of n, but it will be O of n log n, because we'll be sorting the array, right? So the sorting part will obviously take n log n time. So that's one better approach that we can do, since we know that this tree is a BST, that is a binary search tree, right? So that's one property of a BST, that if we basically traverse the BST in n order traversal, okay, that means we first traverse the left hand side, that is the left subtree, then traverse the node, and then if we traverse the right hand side, then that the output of the BST, okay, the output of n order, okay, will always be sorted. Sorted in ascending order, okay, sorted in ascending order. So in an n order, basically we do L and R, where L is the left subtree, N is the node, and R is the right subtree. Alright, so let's see with this example. So if we are traversing from the root, first we'll not print the root, but rather we'll traverse the left hand side. So the left subtree will be 1. Okay, now 1 doesn't have any node, right? It is just null. So the next will be n. That means we have to print the node. So we'll take we'll take the node inside the array and we'll add it. Now next our n is done. So now we'll move to r part. R will be 2. So we'll go for 2. 2 obviously doesn't have any L and R, right? So we'll print the array. We'll add that array inside add the node inside the array. Now for the 3 part, we have completed the left subtree, right? Now we'll print the node. That means we'll add the node inside the array, and we'll go to the right subtree. We'll go to the 4. Now 4 doesn't have any left child, so we'll print the node, will basically add the node inside the array, and it doesn't have a right child. So that, guys, is a sorted array in the ascending order. And now we just have to do a of 1 to find the second smallest element, that is 2. So this way, obviously, we'll be again consuming O of n memory space as we are storing all these nodes inside the array, but our time complexity will be O of n. So we'll not be sorting the array because it is automatically like it is pre-sorted, right? So that will help us greatly reduce the time complexity. But if you notice, right, um, we just wanted the second smallest element, all right? And we know that we got the second smallest element here, that is 2. So why are we actually checking the rest of the elements, that is 3, 4, and so on? Maybe let's say we are having n elements at the right subtree of the 3. So we will still have to check all these elements. That is O of maybe how many elements, like maybe there are 100 elements, so we have to check 100 elements even though we got the 2 in the starting 2, we can say, iteration part, right? So what can be the solution? So what we can do here is we maintain a counter. Okay, we maintain a counter. Okay, and like we will increase initially, obviously we'll keep the counter as 0, and whenever we encounter a node that we'll be adding inside the array, rather than adding it inside the array, what we can do is rather we'll just we'll just um, increment our counter. That means we are traversing that much amount of smaller elements before we are reaching the output. So uh, like I'll just show you the simple iteration part. So we'll do the similar LNR concept, that is the in order traversal. We'll first go to the first element, that is 1. Instead of adding the element inside the array, we'll just increment the counter simply by 1. Okay. Now I'll go to the 2. Now we'll increment the counter 2. Now our k value was 2. That means we want the second smallest element. And the k and counter are matching, right? That means we have reached the second smallest element. So now we'll just break the loop. Okay, we'll break the loop, and there's no need to traverse the rest of the tree as we have already got the second element, and we can just print the node value, right? We can print the node value as we are currently pointing on the second smallest element. So that way, our space complexity will be just O of 1 because we are not storing anything, and our time complexity will again be O of n because if the worst case is that the let's say the smallest element they want nth how many there are 100 elements and they want the 100 smallest element, so obviously we have to traverse all the elements, so it will be O of n. But uh, our average complexity, we can say, have greatly been reduced. So we can say the big O of theta will be reducing greatly. All right. So let's move to the coding part. Okay. So we'll be doing the n-order traversal by using DFS. So we'll define a new function for it. Okay. Inside the DFS, we'll be passing the tree node. Okay. And we also call the function here. Now, once we pass that element, we'll be checking if the node, this will be our base case. So we'll be doing the iterative DFS here. So we'll checking the base case if the node is equal to null. If it's null, then we'll just return. Else, what we can do is we can traverse the left part. So we'll do the LNR concept, right? Left first, then the node, and then the right. So will first traverse the left element, that is node dot left, and then node dot right. But in between this, we have to maintain a counter, right? And we have to check if the counter is matching the key value. So before going ahead, we'll obviously have to define the counter. So, and also we have to pass the key value, because let's say we are incrementing the counter and we are checking when the count, okay, matches key value. We can just return here, right? We can just return, but we have to also return the node value. Now we can't return the node value here because uh, we have to put it a global variable here. Okay, that will be int counter. All right, and because this counter variable, we have to maintain it globally, because we have to keep track of it throughout the DFS iteration part. All right, and also we have to check the key value, but key value is inside this function, so we have to also pass the key value inside our DFS function as well. So we'll pass the value. Okay, we'll also add it here and inside the left and right as well. All right, and now we can't return the value directly, so we can't just so we want the value of node dot val, right? Because this is the result value, because once we reach the element, we need this value, right? So how we can return this value? So we can't just return the value. So what we have to do, because dfs is void, right? So what we can do is maintain a global variable, let's say the result variable. We can update this result variable inside our function. And while returning, what we can do is just return this result variable, because it will be updated with the result value from the DFS function, right? So let's test this. Okay, so it's working properly. Let's submit it. Okay, so it's worked properly. Yeah, thanks for watching.